Hello and welcome to this presentation related to the application of D'Alembert's principle. In this presentation we will consider further problems solved using D'Alembert's principle, but we're specifically going to look at two-dimensional problems where within a particular problem we are resolving forces in both the x and the y directions. It's strongly encouraged that you've seen the two previous presentations related to D'Alembert's principle, the first one being the introduction of the concept itself, and the second one being applications of D'Alembert's principle to solving problems involving horizontal motion or problems involving vertical motion. In this presentation we're going to consider problems involving inclined motion. As with the previous presentations, we'll be constructing free body diagrams throughout, and again for reference there is a separate presentation related to free body diagrams should you need a recap on how they're constructed and used.
And here's a brief overview of the presentation. We commence with a very brief recap of applying D'Alembert's principle. This includes just a couple of slides extracted from our previous presentations. Then question 6b, extracted from our workbook, requires us to calculate an aircraft's takeoff acceleration, labelled A here. To find the acceleration we need to generate two equations, one in the x direction, one in the y direction, to find the accelerations in the x and y direction, from where we can determine the resultant acceleration. Question 7b is a slightly simpler solution to that of question 6b. Here we have to calculate the magnitude of the thrust T from an aircraft's engine. The direction is given in the question. So we just need to generate one equation by considering forces in the x direction. From the equation generated we can calculate the magnitude T. And we will generate an equation in the y direction just to check the value of T. Question 8b. This is very much like question 6b, but it's left for you to produce a solution. So again, we've got to calculate the aircraft's acceleration on takeoff, both in terms of its magnitude and direction. And finally, I'll leave you with question 9b. Here we have to calculate the thrust of an aircraft's engine again, but in terms of both its magnitude t and its direction theta from the horizontal. So unlike question 7b, which is essentially a direct solution by generating a simple equation, we now will have to generate simultaneous equations to find the aircraft's engine's thrust in terms of its magnitude and direction. An overview of the suggested steps required in the solution of question 9 is outlined for your reference. And here are the approximate start times related to various sections contained within this presentation. But as always, please note these are only approximate start times, hopefully to aid your ease of access through the presentation.
Here's an extract from the previous presentation related to applying D'Alembert's principle in the horizontal direction. So just a brief recap here. And from our previous presentations, when we apply D'Alembert's principle, we have to include the inertial force, the MA force. And always remember that the inertial force opposes change in motion. So the acceleration shown here is from left to right. The direction of the inertial force will be from right to left.
And then we effectively apply Newton's first law
of summation of all the forces equal to 0. So this is motion in the horizontal direction. And here's a recap of motion in the vertical sense. Again, we have to apply our inertial force on our free body diagram. And we can summate the vertical forces to 0 here. Again, on this slide, notice the inertial force is opposing the change in motion because the acceleration is up, so the inertial MA force is down. So as I said, those are extracts from the previous presentation where we considered problems involving purely horizontal motion or purely vertical motion. Now I'm going to show you a couple of examples where we're going to consider inclined motion. So essentially we're applying the same principles as you see on these recap slides, but we need to resolve forces into the horizontal and the vertical direction within the problem we're considering. So now I'm going to consider some problems extracted from our workbook, and I'll try and illustrate to you how we now apply D'Alembert's principle to these slightly more complicated questions. So we commence with question 6b. This solution will involve D'Alembert's principle. In our introductory presentation, it was noted that sometimes D'Alembert's principle is not required or even complicates particular problems. And I have to be honest, within the questions I'm going to show, there is no reason to apply D'Alembert's principle here. They could be solved quite straightforwardly using Newton's second law directly. But as required by the syllabus to demonstrate an understanding of D'Alembert's principle applied to engineering problems, we will use the principle here throughout all questions. So question 6b, we have a 26.5 tonne vertical takeoff and landing aircraft which develops engine thrusts labelled P, shown here, and Q, shown here in our sketch. The magnitude of thrust P is 1.8 meganewtons. The magnitude of thrust Q is 243 kilonewtons. And these thrusts are developed during the takeoff phase of In this question, we're asked to calculate the aircraft's takeoff acceleration and its direction given the angle alpha is 70 degrees, so that's the angle of thrust P to the horizontal, and angle beta is 10 degrees, that's the angle of thrust Q to the horizontal. The magnitude of the acceleration is shown here, and the direction from the horizontal is shown here. There is a hint in our question. It suggested we use separate free body diagrams for the horizontal and vertical directions, and so resolve forces horizontally and vertically. From this we can find the acceleration in the x and the y direction, that's the horizontal and vertical directions, and then using Pythagoras' theorem and basic trig, we can find the magnitude and direction of the acceleration A. So I will now outline the solution to question 6b. So question 6b solution, firstly we need to be able to resolve forces from thrust P, shown here, and Q, shown here, into the x and the y directions, or horizontal and vertical components. So considering force P first of all, resolving this into its horizontal component, that will be P cos of alpha, shown here from left to right, and the vertical component is P sin alpha, shown here vertically upwards. Similarly, resolving force Q into horizontal and vertical components, the horizontal component is Q cos beta, that's this component shown here, and the vertical component is Q sin beta, this vertical component here. Again, we've resolved forces into their various horizontal and vertical components in previous presentations. So question 6b solution. Here's my free body diagram showing all the forces acting on the body. Here's our thrust P, angle alpha, thrust Q, angle beta, and of course we need to consider the weight force acts vertically down, symbol W here. If we were to apply Newton's second law directly, which we could, assuming some inertial axes here, then we would simply summate all the horizontal components and equate them to mass times the acceleration in the horizontal direction, and then we summate the vertical components and summate them to mass times the acceleration in the vertical direction. And we could do that. That's a method we could use here and would be perfectly adequate for this particular problem to find the resulting accelerations. However, we have to demonstrate understanding of application of D'Alembert's principle. So here's question 6, again showing a free body diagram, but this time we're applying D'Alembert's principle. So in this free body diagram, we still have thrust P shown, angle alpha, thrust Q shown, angle beta. We still have the weight force acting down, but now we assume body fixed axes and we apply our inertial force, shown here, labelled MA, at angle theta to the horizontal. So when we apply the inertial force to the free body diagram, we essentially have brought a dynamic situation, i.e. the aircraft accelerating on takeoff, into a static analysis. So now we apply Newton's first law and we will summate all the forces in the x direction, or the horizontal components in other words, and we will summate all the forces in the y direction, or the vertical components,
and equate all these forces to zero for the equilibrium condition.
But we must include in our balance the inertial force MA. Again, notice the inertial force is opposing the change in motion, because our acceleration will be in this sense, so the MA force opposes that motion. So now we're going to literally apply D'Alembert's principle in the horizontal, the x direction, and in the vertical, the y direction, and use Pythagoras' theorem to find the resultant acceleration, and use basic trig to find the angle of the acceleration. Question 6b. Here's the suggested solution process to solve this problem. Firstly, to draw a free body diagram of all the forces acting on our body, in this case the body is the aircraft, and because we're applying D'Alembert's principle, remember to include the inertial force, the MA force, on the free body diagram. Remember that the inertial force always opposes the change in motion. Once we're fully aware of all the forces on our body, we can then resolve forces into the x and the y directions. So we can draw another free body diagram, this time of all the forces in the x direction. Because we're using D'Alembert's principle here, we can apply Newton's first law, summation of all the forces in the x direction equals 0. This will produce a simple equation, that's one equation with one unknown, and we can solve this equation for the acceleration in the x direction, that's ax. We can then draw a free body diagram of all the forces in the y direction. And again, applying Newton's first law, this time in the y direction, will generate another simple equation that we can solve for the acceleration in the y direction, ay. Once we know the acceleration is the x and the y direction, we can construct an acceleration vector diagram, as shown here in our right-angled triangle at the bottom of the page. We've now calculated the acceleration in the x direction, denoted ax here, and our acceleration in the y direction, denoted ay here. And so now using Pythagoras' theorem, we can calculate the resultant acceleration, a, which is the resultant vector length shown here, labelled a, where a is equal to ax squared plus ay squared, all square rooted. We can then apply basic trigonometry to calculate the angle of the acceleration from the horizontal, denoted as theta here. And to do that, I would suggest using the tangent function. So tangent of angle theta is equal to the acceleration in the y direction divided by acceleration in the x direction. So that's an outline of the suggested solution process to solve question 6b. I would now encourage you to stop the presentation and attempt question 6b, but I will show you the full work solution on the following slides. Question 6, solution. So extracting the information from the question, the mass of the aircraft, lowercase m here is 26.5 tonne, that's 26,500 kilograms. From this we can work out the weight of the aircraft, that's the mass times gravitational acceleration, so that evaluates to 259,965 newtons for our weight force. Thrust P is 1.8 meganewtons, so P is 1.8 times 10 to the 6 newtons. And that acts at angle alpha, 70 degrees from the horizontal. Thrust P, angle alpha. And thrust Q is 243 kilonewtons. So Q is 243 times 10 to the 3 newtons. And that acts at angle beta to the horizontal, which is 10 degrees to the horizontal. So here's thrust Q at angle beta to the horizontal. So I extracted the information from the question. So question 6b, solution continued. So now we're going to apply D'Alembert's principle within the x direction. So essentially we will now summate all the horizontal components, so p cos alpha, q cos beta, and the max component of the inertial force. And that's what's shown on our free body diagram here. So note our positive notation in this case is rightwards, so forces and accelerations from left to right are positive. We're applying D'Alembert's principle here, that's why the inertial force is shown on the free body diagram, opposing the change in motion. So applying Newton's first law here, because we're applying D'Alembert's principle, summate all the forces in the x direction, they must equal to 0. So summating the forces, we have p cos alpha, that's positive. We have q cos beta, again positive. And we subtract the max inertia force. That all equals to 0 for equilibrium. We're now going to rearrange the equation to find the acceleration in the x direction. On the next line, I've simply added max to both sides of the equation to make it positive. So as written here on the right hand side, I have p cos alpha plus q cos beta. And now I simply divide both sides by m to find ax. So ax is equal to p cos alpha added to q cos beta, all divided by the mass of the aircraft. Inserting the values from our previous slide for the force P, angle alpha, and for force Q and angle beta. The mass was 26,500 kilograms, and evaluating the A in the x direction, this acceleration here is 32.261 meters per second squared. So question 6b, solution continued. We're now going to apply D'Alembert's principle, but this time in the y direction. So now I'm going to summate all the vertical components. So that will be P sine alpha, Q sine beta. The weight force, of course, acts vertically down, and also the MAY force, the vertical component of the inertial force. So that's what's shown on this free body diagram. Notice the positive direction this time is upwards. Positive sense for our forces and accelerations. So summating all the forces in the y direction, they must equal to 0. So for our free body diagram, we have P sine alpha, positive. We have Q sine beta, that's positive. We subtract the weight force because that's acting downwards. And of course we subtract the MAY force because that force is also acting downwards. Again, we equate these forces to 0 because we're applying D'Alembert's principle in the y direction. Very similar approach to solution as for the x direction. I'm simply going to add MAY to both sides of the equation. It leaves me with the P sine alpha added to the Q sine beta minus a W on the other side of the equation. Then we simply divide throughout by m. So AY is equal to the P sine alpha plus the Q sine beta minus W, all divided by m. Inserting the values, the acceleration in the y direction, this acceleration here, is 55.61 meters per second squared. So now we've calculated the acceleration in the x and the y direction, we can now find the resultant acceleration of the aircraft on takeoff. So question 6, solution continued. So now we're going to calculate the resultant acceleration both in magnitude and direction. So to calculate the acceleration's magnitude, labelled A here, is simply Pythagoras' theorem. We know the acceleration in the x direction, we know the acceleration in the y direction. We can work out the resultant acceleration. So inserting the values, that was the acceleration in the x, acceleration in the y. So our magnitude is 64.29 meters per second squared. And to calculate the angle, theta, shown here, angle theta is simply the arctan of the acceleration in the y direction divided by the acceleration in the x direction. Inserting the values, the angle theta is 59.88 degrees, and that's shown as anti-clockwise from the x direction here. So there's the full solution for question 6b, applying D'Alembert's principle to find the resulting acceleration of the aircraft on takeoff. Here's another question extracted from our notes, question 7b, and again we're going to apply D'Alembert's principle to solving this problem. As I mentioned with the previous question, indeed all the questions in this presentation, they can be solved by applying Newton's second law directly, but as we're asked to show understanding of D'Alembert's principle, that's what we're going to apply here. This is a slightly less complicated question than the previous question, but hopefully will engage us in how to draw free body diagrams, how to resolve forces, generate and solve equations. So in this case, a VTOL aircraft develops engine thrusts. That's the forces from the engine labelled T1 and T2. These are shown in the sketch here. There's T1 at angle alpha to the horizontal, and angle alpha is given in the question here, it's 14 degrees. And here's T2, that's at angle delta to the horizontal, and again angle delta is given in the question, 66.2 degrees. The aircraft is in the takeoff phase. In this case, we're given the aircraft's takeoff acceleration, it's 53 meters per second squared, and the angle of the acceleration to the horizontal, that's 58 degrees. The maximum takeoff weight is stated as 27.2 megagrams, and we're actually given the value of thrust T1, it's 0.12 meganewtons. We're asked to calculate the magnitude of thrust T2. We know the angle of thrust T2 from the horizontal, it's angle delta here, but we don't know the actual value, the size of the thrust T2. The answer for T2 is stated in the question to 2 decimal places. So a slightly different approach here to question 6. So let's consider our approach to the solution. So question 7b, here's our suggested solution process. So initially, let's draw a free body diagram of all the forces acting on our body, on our aircraft here. And as we're applying D'Alembert's principle, we must also include the inertial force. Next, we resolve the forces into the x and y axes, shown above. So x and our y axes, that finds the force components in those particular directions. We can then apply Newton's first law in the x direction, and in this case that will actually allow us to solve directly for the thrust or the force T2. What I would then suggest is for practice to apply Newton's law, this time in the y direction, and again solve for thrust T2. You should get the same value within 2 decimal places. So step 4 shown here is really a check on step 3. I would now encourage you to stop the presentation and attempt question 7b, but I will show you the full work solution on the following slides. So question 7b, here's our solution, applying D'Alembert's principle. So firstly, let's draw the free body diagram of our body, the aircraft here. We're clearly given in the question that we have a thrust T1 at the rear of the aircraft at angle alpha, so obviously that's on our free body diagram. And we have a second thrust from the mid-engine, T2 here, angle delta, and again that's on our free body diagram. But don't forget, because we're in a gravitational field, we must have a weight force acting vertically down, so that's my W arrow shown here. And because we're applying D'Alembert's principle, we must also include the inertial force, shown here MA, on our free body diagram, acting at angle theta to the horizontal. And it's drawn in the opposing direction to the change in motion. The aircraft is essentially taken off from left to right, so the inertial force is opposing this change in motion. So this is the free body diagram for question 7b. Just note, within other questions, they may introduce other forces, such as there could be a lift force from the wing in the upwards direction, there could be a lift force from the tailplane in the upwards direction, and there could be an aerodynamic drag force in the horizontal direction that opposes the motion that would need to be added to the free body diagram. With regard to question 7, this is the free body diagram we will now consider as the basis of our analysis. Question 7b, solution continued. Let's extract the information from the question. We're given in the question the maximum takeoff weight is 27.2 megagrams. Now be careful, that's actually a mass. So lowercase m here, 27.2 megagrams. It's actually 27,200 kilograms. That's an SI mass unit. So we need to determine the weight force, W, which is mass multiplied by gravitational acceleration. So our weight force is 266,832 newtons. In the question we're given the thrust T1, shown here on our diagram. T1 is 0.12 meganewtons, or 120 times 10 to the 3 newtons. That acts at angle alpha of 14 degrees, and we're also given angle delta, 66.2 degrees. Here's delta on our diagram. We're also given the takeoff acceleration of the aircraft 53 meters per second squared. Here's acceleration A, and that's at an angle of 58 degrees to the horizontal. So angle theta shown on our diagram here, that's 58 degrees. What I'm going to do is to evaluate the acceleration in the x and y directions, because I will need to use them in the following calculations, because we're going to resolve forces into the x and the y direction. So acceleration in the x is 53 multiplied by the cos 58 degrees. So that will evaluate this vector on our diagram. That's 28.086 meters per second squared. And also evaluate a y on our diagram. That's 53 multiplied by the sine of 58 degrees. So that's 44.945 meters per second squared. And that will be this component here. The acceleration vector diagram is obviously a right-angled triangle. So the question wants us to determine thrust T2, the magnitude of the thrust from the mid-engine of the aircraft here. Question 7b solution continued. We're applying D'Alembert's principle here, of course. We're going to apply it in the x direction. So again, here's our free body diagram of our aircraft. Considering the horizontal components of T1 and T2 here, we're considering all the forces, thrusts, and the accelerations are positive left to right. That's our sign convention. And we're going to summate all the forces in the x direction to equal to 0. That's Newton's first law applied here. So from our diagram, we have positive T2 multiplied by the cos of delta, that's this component here. And we have positive T1 multiplied by the cos of alpha, that's this component here. And we subtract from that the inertial force in the horizontal direction, that's m multiplied by acceleration in the x direction. That has to equal 0 for equilibrium. Transposing the equations, in other words, we're going to add max to both sides of the equation, subtract T1 cos alpha from both sides of the equation, and on the next line we divide throughout by cos of delta. That leaves us with an expression for T2. Inserting our values for the mass, for the acceleration in the x direction, for T1 and cos of alpha, and that's all divided by cos of delta. So evaluating thrust T2 is 1.6045 meganewtons, or 1.60 meganewtons to 2 decimal places. So in this particular question we were able to solve the problem by just generating one simple equation and solve it. Question 7b, solution continued here. Now as a check on the previous calculation, we're going to apply D'Alembert's principle, but this time in the y direction. We should then calculate the same value of T2 to 2 decimal places. Notice this time upward forces and upwards accelerations are positive. So summation all the forces in the y direction equals to 0, Newton's first law. We have T2 multiplied by the sine of delta, this component here, added to T1 multiplied by the sine of alpha, this component here, both in a positive sense. And then we subtract the weight force, that is vertically down, and we subtract the inertial force in the y direction, MAY. That has to equal to 0 for equilibrium. Rearranging the equation, we simply add the MAY to both sides of the equation, and we add W to both sides of the equation, but we subtract T1 sine alpha from both sides of the equation. The subject now is T2 multiplied by the sine of delta, and on the next line we simply divide throughout by the sine of delta. So that results in the equation T2 is equal to mass multiplied by acceleration in the y direction minus T1 sine of alpha plus W. And that's all divided by the sine of delta. Inserting the values, T2 evaluates to 1.59606 meganewtons, or to 2 decimal places 1.60 meganewtons. So we've now checked the value of T2 calculated on the previous slide. So that's the full solution for question 7b. I will leave you with question 8 to solve by applying D'Alembert's principle. In this question, a light aircraft has a mass of 4,893 kilograms and develops an engine thrust, capital T, of 11.5 kilonewtons on takeoff. Engine thrust T shown here. This time the aircraft experiences a drag force, capital D, of 950 newtons, capital D shown here on our diagram, and a lift force, L, generated by the wing. And that's given by the equation lift force L is equal to 1.2 multiplied by W, where W is the weight of the aircraft. So the lift force generated by the wing, shown here acting upwards, and the weight force of the body, shown here acting downwards. So using the above information and also appropriate free body diagrams, we have to calculate the aircraft's takeoff acceleration, labelled A, and its direction, theta. So we're calculating the magnitude of the acceleration A and the angle theta the acceleration makes to the horizontal. Note we're given in the question, angle alpha is 25 degrees, that's the angle of the drag to the horizontal, and angle beta is 15 degrees, that's the angle of the thrust from the aircraft's engine relative to the horizontal. So I'd encourage you now to stop the presentation and try and attempt question 8b. For your reference, the answers are shown in the bracket here. I've stated the acceleration in the x direction, the acceleration in the y direction, and the resultant acceleration, and the angle the acceleration makes with the horizontal. Question 8b. Here's the suggested solution process to solve this question, very similar to that we used for question 6b. More forces here to consider in our balance. But as I say, I would encourage you to stop the presentation and attempt question 8b, and I'll let you develop your own solution to the process. Note the answers again shown here for your reference. I'll also leave you with question 9b. We've got to find thrust F1 that's required. So essentially what we have to do now is to find the value of F1, both in terms of its magnitude F1 shown here and its direction theta1 shown here. Question 9. Here's the suggested solution process, which would involve generation of simultaneous equations. So as always, firstly draw the free body diagram of all the forces acting on the body, on our aircraft here, and because we're applying D'Alembert's principle, then add the inertial force to the free body diagram. That will allow us to resolve the forces into the x and y directions, the horizontal and vertical axes. So now we can draw a free body diagram in the x direction only, considering the x components, x direction forces, and we can apply Newton's first law of motion. I would suggest label it equation 1 for force F1 in terms of cos theta 1. So in other words, F1 on the left hand side of our equation will equal some expression involving cos theta 1 on the right hand side. There will be two unknowns in that equation, F1 and theta 1, so we cannot solve the equation. We need to generate a second equation. And we do this by drawing a free body diagram in the y direction, consider all the forces in the y direction, and then apply Newton's first law in the y direction. This will generate a second equation, which I suggest call equation 2. And again, we can rearrange the equation for F1 in terms of cos theta 1. What we're going to do now is to solve the simultaneous equations. So we're going to equate equations 1 and 2 above. This will eliminate the F1 term from the equation, so we can solve for angle theta 1. Just note that within this solution, when solving for theta 1, we will need to divide the equation throughout by cos theta 1, and then you will note this will allow the equation to be solved using a single tan theta 1 function. It's a technique we've used in previous presentations for solving trigonometric equations. Once the value of theta 1 is found, we can back substitute theta 1 into any of the equations. I'm suggesting here equation 1, and that will allow us to solve for the value of the thrust or force F1. So that's the suggested solution process for question 9b. Slightly more complicated in the latter part of the solution process because the transposition is slightly more difficult. So again, I would encourage you to stop the presentation and attempt question 9b. As I said at the beginning, these questions could quite easily be solved and probably preferably be solved by applying Newton's second law directly, summation of all the forces equals to ma. But as the syllabus requires us to show understanding of D'Alembert's principle, then I've used D'Alembert's principle in these solutions. You will find in later presentations where we're considering rotating masses, when we're considering out of balance problems, flywheels, etc., D'Alembert's principle is of use to engineers in the analysis of such problems. I hope this presentation has been of use to you, and as always, thank you for viewing.